Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 4.7 from your textbook, which introduced you guys to the concept of an ordered basis and also the representation of a vector corresponding to a given ordered basis. In the previous video, we sort of hinted at the idea that if you have several ordered bases, you might want to sort of know how to transfer from the component representation under one basis to the component representation in a different basis. And we sort of stated that this can be done through some clever matrix operations. So we're going to get right into sort of seeing that. We're going to give a definition of what is called the change of basis matrix. We're going to see that that change of basis matrix basically allows you through matrix multiplication to convert from the component representation in one basis to the component representation in a second basis. And we're going to look at an example of doing that. Now, just like some of the other parts here after we got out of sort of bases, we're going to do this pretty quickly. We're going to focus on making sure you guys see an example of this. We're not going to get too far into the sort of mechanics behind it because, again, this is a little bit of a tangent from the main flow of our class. But let's go ahead, state this definition, and take a look at an example here. So, definition, let's let V be an n-dimensional vector space with two different ordered bases, B1 and B2. And we're specifically going to say that B1 consists of the vectors V1, V2 through Vn. So then the matrix P with this B2 with an arrow coming from B1, this matrix here, which we call the change of basis matrix from B1 to B2, is defined as the component vectors, the column vectors, right? Remember, anytime you're talking about the component representation of a vector relative to a basis, we think about it as a column vector. So this matrix is made up of these column vectors, right, where we take each of the vectors from basis 1 and represent it in terms of B2. So this change of basis matrix is all of the sort of component representations of the vectors in B1 relative to B2. Then this matrix will have the property that if you do matrix multiplication of this matrix times a vector that is in component form relative to B1, the result will be that same vector's representation relative to B2. And hopefully this also explains the sort of weird subscript of B2 with that left arrow and B1. It's so that you can sort of see how the B1s align here, and then you use that notation to realize you're going to be landing in B2. Now, your textbook gives some background about exactly why this format will cause the matrix to have this property. Again, for me, I feel like that's a bit of a sort of tangential part of the class. So you guys can read that explanation if you want, or you can sort of take this on faith and sort of understand how the example works and use that as a justification. But if you do want to see the proof, it is in your textbook. One sort of note that should sort of make sense, I believe, again, your textbook proves this, but it's sort of interesting. If you were to build this change of basis matrix, the one that goes from B2 back to B1, as a matrix, this will actually turn out to be the inverse of the original change of basis matrix. And that should sort of make sense, right? Is that if you want to go the opposite direction, if you want to start from B2 and work your way back to B1, then you just need to use the inverse of the matrix that we're going to learn how to build. So that's sort of an interesting fact, and it tells you that, you know, moving between bases really acts the sort of way that you would expect. So, since we're not going to go too far into the details here, let's take a look at an example of sort of taking a space that has a couple different bases, representing a vector in terms of one of those bases, then building the change of basis matrix, and then confirming that the change of basis matrix actually does do what it claims to do, which is get the component form in the other basis. So let's go ahead and do that. So here's our example here. We're going to be working in M2 of R, so the space of 2 by 2 matrices. B1 is going to be this basis, which is 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, and 1, 1, 1, 1. Again, I'm not going to prove that that is a basis. It certainly has the right amount. We know that the dimension of M2 of R is 4, and we've got 4 vectors here. You would need to prove on your own that this is linearly independent, and that'll assure that it's also a spanning set since the dimension equals the number of vectors. And then our second basis is going to be this thing that's 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, negative 1, and 0, 1, negative 1, 0. Once again, it has the right amount, but it would be something that, you know, you should show if you were doing this completely formally, that this also is a linearly independent set, which would guarantee that it is a basis for M2. Don't worry, though, both of these actually are bases. I'm just not taking the time to sort of demonstrate their linear independence. Then we're going to let V be a random vector out of M2 of R. For the sake of this example, it'll be the 2, 3, 3, 1 vector. What we're going to do is we're going to first represent this guy in terms of B1. Then we're going to determine the change of basis matrix to go from B1 into B2. And then we're going to combine these two things to figure out how to represent this in terms of B2. And then once we do that, we'll check that that representation that comes from using these two really is correct, which hopefully, even though we're not going to do the formal proof, will demonstrate that the change of basis matrix really has the property we claimed on the previous sort of page. So let's get it right in and try this out here. So for A, determining this guy, so we need to sort of figure out what 2, 3, 3, 1 in terms of B1 is going to look like. So we're going to need to set up the equation C1 times the first thing in B1, which is 1, 0, 0, 0, plus C2 times 1, 1, 0, 0, plus C3 times 1, 1, 1, 0, plus C4 times 1, 1, 1, 1, and that is going to need to equal this guy right here. Right, so that'll be 2, 3, 3, 1. Now, hopefully that we've done enough of these examples already that you guys can sort of follow along. If we skip the step of actually writing out the system of equations, we're going to jump right to the augmented matrix. So what does the augmented matrix that corresponds to this look like? Well, it looks like we should get 1, 1, 1, 1, and then augmented to 2. That's taking this guy, this guy, this guy, this guy, and setting it equal to that. And then so on. So then it looks like we should get 0, 1, 1, 1 has to be 3. That's taking this guy, this guy, this guy, this guy, and having it be that. Then it looks like we should get 0, 0, 1, 1, 3. And then finally 0, 0, 0, 1, 1. Okay. Now, if you notice, as soon as we put it into this augmented form, we could mess around and try to do more with it, but this is actually already in row echelon form. So we might as well just back solve immediately, and this should be pretty quick. We should get that C4 needs to be 1. We can get that C3 plus C4 needs to be 3, which means that C3 plus 1 needs to be 3. So C3 needs to be 2. Then we should get that C2 plus C3 plus C4 needs to be 3. So that means C2 plus 2 plus 1 has to be 3. So that looks like C2 needs to be 0. And then finally C1 plus C2 plus C3 plus C4 is supposed to be 2. That's C1 plus 0 plus 2 plus 1 equals 2. So C1 is negative 1. So what we're saying here is that this matrix, 2, 3, 3, 1, if we want to represent it in terms of B1, we can think about that as the component vector minus 1, 0, 2, 1. In other words, we are saying we need negative 1 times the first basis element, 0 times the second basis element, 2 times the third basis element, and 1 times the fourth basis element to create this guy here. And if you want on your own, you can check that minus 1 times this guy, 0 times this guy, 2 times this guy, and 1 times this guy really does give you that, right? But this is the correct component vector representation. Okay, so that was doing part A. We figured out how to represent this thing in terms of B1. Now, would it be hard to just jump ahead to C and do the same thing for this? No, absolutely not, right? We do the same thing, except we'd set these guys to be these here. But what we'd like to do is we'd like to have a sort of way of doing this in general, right? Rather than resolving the equations each time. So instead of just jumping right to here, we're actually going to create this change of basis matrix. And the reason I mention this right now before we get into building it is that this is going to take a lot of work. And so like when we're doing it in a single example, it doesn't really seem to make sense in terms of workload to build this and use this to get this guy rather than just jumping to this guy right away. But if you had lots of vectors to convert, or you just wanted to understand in general how to convert from one to the other, then this guy becomes a lot more warranted. But let's go ahead and think about how we're going to do this. So we'll go ahead and take a look at that on the next page here. So for part B, right, we would know that P that goes from B1 into B2, what that's going to look like is each of the things in B1 represented in terms of B2. So that would be the representation of 1, 0, 0, 0 in terms of B2. Then it would be 1, 1, 0, 0 in terms of B2. Then it would be 1, 1, 1, 0 in terms of B3. And then in terms of B2 there's no B3 here. in terms of B2. And then finally, 1, 1, 1, 1 in terms of B2 as well. Okay, so what that means is we're going to have to solve for the component representation of each of these four things to build this matrix. So let's go ahead and start with this first one here. So for this first one, we're going to have to take C1 times 1, 0, 0, 1 plus C2 times 0, 1, 1, 0 plus C3 times 1, 0, 0, minus 1 plus C4 times 0, 1, minus 1, 0. And we're going to have to set that equal to 1, 0, 0, 0. Okay, now let's go ahead and immediately move that into the augmented form. So it looks like we should get 1, 0, 1, 0, and 1. Then 0, 1, 0, 1, and 0. Then 0, 1, 0, minus 1, and 0. And then finally 1, 0, negative 1, and 0, 0. Okay, now one thing I want to point out to you guys is that when we go to do these other ones here, this part of the augmented matrix, which came from understanding these guys, will not change. So when we go to redo this, we can jump immediately to this and only modify this depending on which of the three we're working on. All right, to solve this, let's go ahead and just quickly do R4 and replace it with R4 minus R1. So it looks like we should get 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, minus 1, 0, and then 0, 0, minus 2, 0, and minus 1. Okay, then we can do one more operation. This guy can remove this here. So we can do R3 and replace it with R3 minus R2. So it looks like we should get 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, negative 2, 0, and then 0, 0, negative 2, 0, negative 1. Okay, now technically we should probably do one more operation, which is to interchange R3 and R4, but I think you guys are comfortable at this point sort of back solving even if it's not perfectly in the right form. We'll just be careful here. So we should get that negative 2C3 needs to be negative 1, which immediately gives us that C3 is 1/2. We should also get that negative 2C4 is 0, which means that C4 is 0. Then we should get C2 plus C4 is 0. Since C4 is 0, this means that C2 is also 0. And then we should get that C1 plus C3 is equal to 1. Since C3 is equal to 1/2, that looks like C1 should be equal to 1/2. So this tells us that the first element that, what was that 1, 0, 0, 0, in terms of B2, is actually equal to the component 1/2, 0, 1/2, 0. This is where we got to be careful since I solve these out of order. I got to make sure that this guy ends up at the end and this guy ends up in the third spot. Okay, so that's the first one. Now, like we sort of said, to do the remainders, we should be able to do this a bit more quickly because we can sort of start with this and just modify this guy based on which of these we're solving. Notice when we go to solve this guy, this should change to 1, 1, 0, 0. When we go to do this guy, it should be 1, 1, 1, 0. And when we do this one, it should be 1, 1, 1, 1. Okay, so let's go ahead. We'll grab this guy so that we don't have to rewrite everything. And let's go ahead and do that on our next page. So go ahead, pop that guy right there. And like we said, the only thing that we need to modify is to change this guy into a 1. Because now we are solving for this guy here, and those first two components, this guy and this guy, both need to be 1. All right, same elementary row operations should do well here. Let's try to actually do several together. Let's do row 4 and replace it with row 4 minus row 1. And let's also take row 3 and replace it with row 3 minus row 2. So we're going to get 1, 0, 1, 0, and 1, and then 0, 1, 0, 1, and 1. Then we should get 0, 0, 0, negative 2, and negative 1. And then we should get 0, 0, negative 2, and 0, and negative 1. Once again, once we do that, we should be immediately ready to sort of back solve, even though it'll be a little bit out of order. We get negative 2C3 is negative 1. So C3 looks like it's going to be 1/2. We get negative 2C4 is negative 1. So C4 is going to be 1/2. Then it looks like we get C2 plus C4 is supposed to be 1. Since C4 is 1/2, then C2 also must be 1/2. So C2 is 1/2. And then we get C1 plus C3 needs to be 1. Since C3 is equal to 1/2, then C1 must also be 1/2. So C1 equals 1/2. So what this tells us is that the representation of 1, 1, 0, 0 in terms of basis 2 is actually the component where you use 1/2 of every vector in B2. Okay, so that's another one. Let's go ahead. We'll grab this guy again. And we'll try this again. All right, so now we're going to be representing the third basis element, so this guy here. Notice that's going to be 1, 1, 1. So this time we got to modify this guy to a 1. So, okay. So we'll do the same sort of set of operations. We'll take R4 and replace it with R4 minus R1. And we will also take R3 and replace it with R3 minus R2. So when we do that, we get 1, 0, 1, 0, 1, and we get 0, 1, 0, 1, 1. When we take this guy away from this guy, it looks like what we should get is 0, 0, 0, negative 2, and 0. And then here we should get 0, 0, negative 2, 0, and negative 1. We can immediately start our back solving again. So we get negative 2C3 is negative 1. So it looks like C3 has got to be 1/2. Then negative 2C4 needs to be 0. So C4 is 0. Then we get C2 plus C4 needs to be 1. Since C4 is 0, looks like C2 should be 1. And then finally, we get C1 plus C3 is equal to 1. Since C3 is 1/2, that means C1 needs to be 1/2. So C1 equals 1/2. So this means that the representation of 1, 1, 1, 0 in terms of B2 is actually equal to the component 1/2, 1, 1/2, 0. Okay, and again, that's just making sure that we're careful. This guy has to go in at the end. This guy has to go third there. Okay, so we've got one last one to do. Once again, we'll just try to reuse as much as possible there. Okay. And one last time here. Okay, so now we're doing the fourth vector in B1. So this guy, that means all of these need to be 1. So let's go ahead and modify that. So all of these are 1. Same thing, R4 replaced with R4 minus R1, R3 replaced with R3 minus R2. We get 1, 0, 1, 0, and we get a 1, and we get 0, 1, 0, 1, and we get a 1. Then we should get 0, 0, 0, negative 2, 0, and we should get 0, 0, negative 2, 0, 0. Solving that, looks like we get negative 2C3 is 0, so C3 is 0 this time. Negative 2C4 is 0, so C4 is 0. Then we get C2 plus C4 must be 1, so that looks like C2 must be 1. And finally, we get C1 plus C3 must be 1. Since C3 is 0, C1 must be 1. So the representation of 1, 1, 1, 1 in terms of B2 is actually the component vector 1, 1, 0, 0. Okay, so each of these component vectors, let's just go back and take a look at them, right? Each of these component vectors here make up the columns, right? Each of these guys is the columns, or are the columns, who knows what the grammar is there, right? And each of these are the columns of that change of basis matrix. So let's go ahead and write out that change of basis matrix. I'll just grab each of these individually so that we can do this a little bit faster. That guy was our first one, so this was where we actually started it, right? So this guy right here, right? That was one of them. We'll put this at the very end, okay? So we got that guy. Then this looks like when we did the second one. Okay. All right. Then we got the third one right here. Okay. And the fourth one right here. Okay. So what this then tells us is that the actual solution to the change of basis matrix that allows us to go from things represented in B1 into things that are in B2 is this matrix that is 1 half, 0, 1 half, 0, 1 half, 1 half, 1 half, 1 half, 1 half, 1, 1 half, 0, and 1, 1, 0, 0. Okay, so a tremendous amount of work, but now we know how to transition from anything that's represented in basis 1 into basis 2. So let's put this to use here, right? So we want to determine V in terms of B2. So to do that, we would say that V in terms of B2 is the matrix that we just created, 1 half, 0, 1 half, 0, 1 half, 1 half, 1 half, 1 half, 1 half, 1, 1 half, 0, and 1, 1, 0, 0, times the representation in B1, which we did at the very beginning, right? That was the very first thing that we figured out, right? Right back here, this was how you represented the vector that we're interested in terms of this. So let's just grab this guy as well. All right. So we pop that guy right there. Guess we don't need that. Okay, so we're just going to do some matrix multiplication now. We're going to take each row of this times each column of this. So if we do that, looks like we should get negative 1 half, and then a 1, and then a 2. So let's see, that's 1, 2, negative 1 half. So it sounds like a 3 halves up there. Then it looks like we should get a 3. Then it looks like we should get negative 1 half, a 1, so a 1 half. And then finally, the last guy is just going to be a 0. So there we go. So according to this, the representation for this vector V in terms of B2 should be 3 halves, 3, 1 half, 0. Can we do a check of this? Well, sure, right? This should confirm, hopefully, that this really does work. Well, let's actually do 3 halves times the first thing in B2. First thing in B2 is that 1, 0, 0, 1. So 1, 0, 0, 1 plus 3 times the second thing, which is that 0, 1, 1, 0 plus 1 half times it looks like 1, 0, 0 minus 1. And then finally nothing times the last guy, which is that 0, 1, negative 1, 0. Okay, let's go ahead and see. First component should be 3 halves and then a 1 half. So 3 halves and 1 half, that sounds like it's going to come out as 2. Does that look good so far? Yes. Second component, well, that's going to be 0. Looks like we're going to get a 3, and that's it. So we should get a 3 there. Does that look good? Yes, it does. Then we can go ahead and do this guy. That's going to be 0. We're going to get a 3, and that's it. Does that look good? Yep, it absolutely does. So we get a 3 there. And then finally, bottom component, right, the 2, 2 component, we get a 3 halves. We get a negative 1 half. 3 halves and negative 1 half sounds like a 1. There we go. Is that actually the vector? Yep, 2, 3, 3, 1. Check. So what that shows you now is that if you represented anything in terms of B1, simple matrix multiplication by this would immediately give you the representation in B2. On your own, you could also, for fun, invert this matrix. It will be invertible. And if you invert this matrix and multiply it by something like this, then you would take the inverse of this with something represented in B2, and it would give you the result, which would be in B1. So this basically shows you guys that there's a sort of deep relationship between matrix multiplication and specifically matrix operations in general and converting between different sort of representations under different bases. In the next video, we're going to continue with sort of another slight tangent, just trying to find out some other interesting things about matrices and how they relate to bases in different subspaces. And we're going to discuss some subspaces that can be generated by understanding the rows and columns of our matrix.